Hi everyone, Dr. Burns here with our next lesson in our acids and base chapters. Today we're going to be talking about polyprotic acids. Now, polyprotic acids are acids that have more than one proton that can ionize in solution. So poly means multiple. So they undergo multiple ionizations, and with each new ionization, a new Ka can be calculated or can be determined. So if you look in Appendix 4 of your textbook, there are some acids that are in there that have multiple Kas. They have a Ka1, a Ka2, some even have a Ka3 because they can do multiple ionizations. So there's 3 different types of polyprotic acids that we can discuss. What we've been working with so far are monoprotic acids, meaning that they have one ionizable proton. So this is something like HF, HCl, HNO3. They only have one hydrogen that can ionize in the solution. We then have a diprotic acid, which is 2 ionizable protons, di meaning 2. So this is something like H2SO4 is a diprotic acid. There's a couple others like carbonic acid, H2CO3. So they have 2 hydrogens that can come off, that can ionize. And finally, we have triprotic acids, which have 3 ionizable protons, tri meaning 3. And a big example of this is H3PO4. Phosphoric acid is a triprotic acid. So we see 3 hydrogens that are able to come off and ionize into solution. So the ionizations of those hydrogens don't happen all in one step. The definition of an acid is that it gives away 1 proton, it donates 1 proton. Therefore, each ionization gives up 1 proton. So if I have a monoprotic acid, it's only going to ionize once. If I have a diprotic acid, it's going to have 2 separate ionizations. If I have a triprotic acid, it's going to then ionize 3 times. With each one, you see 1 less hydrogen on that acid. So here I have carbonic acid. We start with H2CO3 and we take off 1 hydrogen. So just 1 of these hydrogens comes off and we're left with HCO3-. So this is the first ionization. The second ionization then has the HCO3- as the reactant now, because this hydrogen is now going to come off and create H+ and CO3 2-. You know the reaction is done and all of the ionizations have happened when your product has no hydrogens left over to give away. So with each of these ionizations, we have a different K value, a different ionization constant, because they're different reactions. So the first one, we have H+ and HCO3- over H2CO3. That is considered Ka or Ka1 because that is the first ionization. Then we have Ka2, which now has H+ and CO3 over HCO3-. So for any given acid, the first ionization constant, that Ka1, is always going to be much larger than the second. If there was a third one, then that would be even smaller. Because with each ionization, the acid becomes weaker and weaker. So the best way to learn about polyprotic acids and how to solve these types of problems is to just do one problem. Since we have 2 ionizations of weak acids, you're essentially treating each ionization as its own equilibrium expression and as its own problem. So you're just doing equilibrium problems over and over for the same problem. You'll do the first ionization, do an ice table, you'll do the second ionization, do an ice table, and that will give you the final result. So let's look at another diprotic acid, which is oxalic acid. We know it's a diprotic because it has 2 hydrogens there. So oxalic acid is a poisonous substance that's used mainly as a bleaching agent. we want to calculate the concentration of all species present at equilibrium in a 0.1 molar solution at 25 degrees Celsius. So we're looking for the concentration of H2C2O4. We're also looking for the H plus concentration, and then we're also looking for the concentration of oxalic acid after it's lost one of its hydrogens. So we have HC2O4 minus, as well as C2O4 2 minus. Those are all of the species that we're looking for concentrations of. How do we know that? Well, we look at its two ionizations. So our strategy for solving this problem is to follow the same procedure for each ionization as for the determination of the equilibrium concentrations of a monoprotic acid. You're essentially treating each ionization as a monoprotic acid reaction. All of the reactions that we've looked at in our previous lesson, talking about weak acids and weak bases, those were all monoprotic acids. Then the conjugate base resulting from the first ionization, so this guy here, is then the acid for the second ionization, and its starting concentration is the equilibrium concentration from the first ionization, which we'll get into what that means. So the first thing that you want to do whenever you're faced with these problems is to write out those ionizations. You know that you're either going to have 1, 2, or 3 ionizations going on, depending on what the acid is. So since oxalic acid is diprotic, we're going to have 2 different ionization expressions. So our first one is here. We have oxalic acid removing 1 hydrogen and creating HC2O4 minus. And then we also have our second ionization where our conjugate base here is now used as a reactant, and we get H plus and C2O4 2 minus. For these problems, I do strongly suggest just ignoring water because then it's just another column in your ice table that is just not needed. We know it's not going to contribute to anything in the problem itself. So if you just ignore it, it becomes a lot easier to see what we have to do for these problems. So the next thing that we want to do is construct an equilibrium table for each of those ionizations. We're going to use, because we're going to have 2 different ice tables, we're going to have one where we have the change in terms of x, and then one as the change in terms of y, just so that we're not getting our x's and or anything mixed up in our 2 ice tables. So here are what our ice tables look like for each of those ionizations. We have our first ionization here and our second ionization here. So in our first ionization, we know our initial concentration is 0.1. From the problem, we know our initial concentrations of our products are going to be 0. We know that our change column is going to be set up as minus x plus x plus x. We learned that in our previous lesson about weak acids. And then we just add those 2 columns up. Now when it comes to our starting concentrations of our second ionization, we can't just start with 0.1 again here, because then we're just doing the same ice table over and it's not really showing anything. Now, in order to understand what we're doing in these ice tables, you have to remember that this ionization, these 2 consecutive ionizations, are happening all in the same container. So as my oxalic acid breaks down into H plus and HC2O4, I immediately have some level of concentration of those 2 products, and that is the variable x. So that's the first ionization. Now my HC2O4 minus is going to then ionize again, so its concentration is now going to change. And the H plus concentration, as we can see from our 2 ionizations, is another product. So we're going to be adding even more to that concentration. So the equilibrium concentration of the hydrogen oxalate, the HC2O4 minus, after the first ionization becomes the starting concentration for the second ionization. Okay, so whatever's here in these 2 columns from our first ionization then gets put in the initial row of our second ice table. Okay, we still have concentrations of those. We've now, after our first ionization, we've built up those concentrations Okay, so we still have to account for those. And then once we have those initial concentrations in, then we treat the ice table in the same way that we do any weak acid problem. Our change is still minus y plus y plus y. I'm using y's instead of x's just so I'm not mixing them up. And then we add those two columns up into our equilibrium. Whatever we get here in the second ionization H plus column is then going to be what we use to find pH. If we were asked to do that, which some of these polyprotic acid problems ask you to do. They say, what is the pH at equilibrium? Well, it's not this value, it's actually this value, because you have to account for the ionization twice. And they don't happen the same amount. It's not like we can take that initial value and multiply it by 2 or anything like that. Okay, so we have to account for it twice using two ice tables. So now once you have your two ice tables set up, you just do the first one, solve for your x values in our normal way, and then you do your second. So let's take this first one here. We're going to plug these values into Ka. Oxalic acid has a Ka of 5.0 times 10 to the minus 2. You can get that from your Appendix 4 or from your Alex data table. You'll see Ka1 and Ka2. Please just make sure you're using the correct one for the ionization. So Ka1 is 5.0 times 10 to the minus 2. And that's going to be equal to x squared over 0.10 minus x. Now the one downside about a lot of these polyprotic acids is while they have multiple Kas and a lot of those Kas are small, usually the first Ka, so Ka1, is large in comparison, so we usually can't use our x trick. We can't assume that x is negligible, at least for the first ionization. The second ionization almost always has a Ka that's small enough to do that assumption, but the first one is usually one where you have to use the quadratic equation. So we can go through this and solve to get this into a quadratic form. So we would get x squared plus 5.0 times 10 to the minus 2 minus 5.0 times 10 to the minus 3, and that's going to be equal to 0. And then we can use the quadratic equation to solve for that. Now we don't want to do anything with our second ice table yet because we don't know these initial concentrations. So let's move on to solving for that first x value. So here's everything that I just wrote. We have our Ka expression, we have our quadratic form. You can use the quadratic equation or your solver button on your calculator in order to solve for x, but essentially what we get is that the H plus concentration and the H2CO4 minus concentration is both 0.05, and then we plug that x in to our H2C2O4, our oxalic acid column, to get that its equilibrium concentration is 0.05 molar. So if I go back, that means that x here is 0.05 and 0.05, meaning that when I start my second ice table, I'm going to plug in 0.05 and 0.05 in for that second table, because now I know what my initial concentrations are of H plus and HC2O4 minus before the second ionization starts. So we can plug that into our ice table here. So that's what I did here. And now once we have that initial concentration, we can then solve this ice table in the same way that we've done for our previous ice tables. So we have our Ka set up. Ka2 is 1.6 times 10 to the minus 5, and then we plug everything in from our equilibrium row there. Now our Ka is small enough where we can see those changes in y as negligible, which makes solving this problem a lot easier, because this basically comes down to 1.6 times 10 to the minus 5 is equal to 0.050y divided by 0.050, which we know that if we have the same thing on the top and the bottom, they cancel each other out. So y is equal to 1.6 times 10 to the minus 5 molar. So that's what we would plug in here, and we wouldn't need to plug it in here or here because we saw those changes as negligible. So that then gives us our equilibrium concentrations of the H2C2O4, the H+, as well as the C2O4 2-, which is what we were looking for. So let's summarize that last point there. We filled in our ice table, we solved for y because we saw these as negligible, and then the 0.05 canceled on top and bottom, meaning that the H2C2O4 concentration was equal to 0.05, which we solved in our first equal ice table. We then used y, we canceled out y in both the H2CO4- and the H+ column, so their concentrations are also 0.05. And then we plug in y for the C2O4, so that's the 1.6 times 10 to the minus 5 value there. So again, it's just two equilibrium problems, two weak acid problems. The only thing that we have to remember is that the equilibrium concentrations from the first ionization then become the initial concentrations for the second ionization. That's all that we have to do. There is nothing different in what we did except for plugging in initial concentrations for our second ionization. So let's do another practice problem with that. Here we're asked to calculate the concentrations of H+, HCO3-, and CO3 of a 0.025 molar H2CO3 solution. So we know that we're going to have two ionizations because we have an H2 here. So the first thing that we want to do is set up our first ionization and our first ice table. So we know that H2CO3 is going to first ionize to H+ and HCO3. So one hydrogen comes off in the first ionization. So that's the first part of our problem. We're not even going to worry about the second part right now because we're taking these each as their own individual weak acid problem. So we'll set up our ice table in the same way that we have. We know our initial concentration of H2CO3 is 0.025. The initial concentrations of our products are 0. Our change is the same as our other weak acid problems. So we get 0.025 minus x, x, and x. So then we can start solving for that x value. So we have Ka, which is 4.2 times 10 to the minus 7. Is equal to x squared over 0.025 minus x. Because our Ka is small, right, it's 4.2 times 10 to the minus 7, we can see that as negligible, that x. So that makes solving for our x here a lot easier. So we're going to have 4.2 times 10 to the minus 7 is equal to x squared over 0.025. So now let's grab our calculators and solve for x together. So we'll take 4.2 times 10 to the minus 7, and we'll multiply that by 0.025. And I get x squared is equal to 1.05 times 10 to the minus 8. We can then do the square root of that value and solve for x. So we get x is equal to 0.000102, and that's a molar concentration. So that is then the concentration of HCO3 minus, forgot a minus there, oops. It is also the concentration of H+, not at equilibrium because we still have another ionization to go. So we have now that we solved for X, what we can do is now start our second ionization. So we will take that HCO3 minus, and it is then going to ionize into H plus CO3 2 minus. So now we're on to our second ionization, and we're just going to make another ice table. Again, no different to how we've done any other ice table problem in the past. Same thing that we've done. The only difference comes from when we solve for our initial. So we take what's in this row and we bring it down here. So HCO3 minus had a concentration of 0.000102, and H plus had a concentration of 0.000102. We're adding to that concentration in our second ionization. I had some in my first, and I'm going to have more in my second. The initial concentration of the CO3 2 minus is 0 because we haven't ionized that hydrogen yet. Okay, so now we set this up in the same way. We do minus y plus y plus y. We get 0.000102 minus y. We get 0.000102 plus y, and we get y. And now we plug in for our Ka again. So we have Ka for Ka2 is 4.8 times 10 to the minus 11. So 4.2 times 10 to the minus 11, 4.8, sorry. 4.8 times 10 to the minus 11 is now equal to y times 0.000102 plus y divided by 0.000102 minus y. Our Ka is small again, so we can see this y is negligible and this y is negligible. Again, any changes in y we can see as negligible if Ka is small. So we can rewrite this to be 4.8 times 10 to the minus 11 is equal to y times 0.000102 divided by 0.000102. Just like we saw in our previous problem, those two values are going to cancel, and we get that y is equal to 4.8 times 10 to the minus 11. So that then means that the equilibrium concentration, let's see, we were asked for H plus, HCO3, and CO3 2 minus. That means that H plus at EQ, HCO3 at EQ, and CO3 2 minus at EQ. That's then equal to, let's see, H plus, we see that y is negligible, so its concentration would be 0.000102. The same goes for HCO3 minus, 0.00102. Those are all molars. And then for CO3 2 minus, it's equal to y, so its concentration is 4.8 times 10 to the minus 11 molar. So you're going to start seeing a pattern with these types of problems, especially with the diprotics. Triprotics are a little bit different. I have another video available on e-learning that goes through a triprotic acid. It goes through phosphoric acid. I give you a practice worksheet and we can do the first problem together, and then you have another problem after that that you can try independently. I strongly encourage you to go through that video. It's not for any points. You don't have to go do that worksheet if you don't want to, but if you want some extra practice with these problems, feel free to do that one.